As you might remember from the alkyne chapter of Organic Chemistry 1, anytime you have an aldehyde or a ketone, it exists in equilibrium with what's called an enol. So for example, in this case, they're giving us cyclohexanone. So we have a 6-membered ring, cyclohex, all single bonds, AN, and then a ketone, ONE. They don't tell us where to put the ketone because no matter where we put it here, the molecule's the same. You could sort of rotate this like a dial and put the ketone on any other position. And so it's the same no matter where it is. So anytime you have an aldehyde or a ketone, you always have some sort of an equilibrium between the ketone and what's called an enol. Now it's called an enol because you have a double bond and you have an alcohol. And they're right next to each other. So that is an enol. And if you look at the difference between these structures, the real difference is just the position of one hydrogen and also where electrons move to allow the hydrogen to move. There are 2 hydrogens on this carbon here. There's only one in the product. The other one jumped onto the oxygen. So if two molecules are the same, except for where one hydrogen is placed, the relationship between those 2 molecules is called, that relationship is called Tautomers. This is all one word, Tautomers. So Tautomers are 2 molecules whose only difference is the position of one hydrogen. And so you have a ketone, you have an enol, and so this is called keto-enol tautomerization. When one of these transforms into the other. And the place you would have heard of this before in Organic Chemistry 1 was when you do hydration onto an alkyne. So whether you do acid-catalyzed hydration or hydroboration oxidation onto an alkyne, you would remember that after you add the H and OH, it undergoes keto-enol tautomerism to give you an aldehyde or a ketone. So that would be from that previous semester. And if you don't remember that, I have videos from Organic Chemistry 1 I'd be happy to send to you if you reach out to me on that. And so here, they just want to show you how these transform, why these are always existing in equilibrium. And because it's just a difference of one hydrogen, or a hydrogen changing place, you can see that this mechanism is only going to involve proton transfers. We're going to take a proton off of this alpha position, we're going to put it onto the oxygen. I say alpha position, remember that the carbon that has a double bond is the carbonyl carbon, and the one right next to it is the alpha carbon. So those hydrogens are in the alpha position there. Okay, well, what are we going to use to do our proton transfers? They said that it's acid-catalyzed. So we'll take our ketone, and what we're going to add to it is hydronium, because it's acid-catalyzed. So whatever strong acid we throw into water, it'll give its H pluses away, and water will become H3O+. Water will accept those. And we've seen before how this oxygen in the carbonyl is slightly nucleophilic. It can kind of act as a base. It has a slight negative charge. And so we've seen it in previous mechanisms how it can steal that slightly positive hydrogen and hydronium, and the electrons snap back onto the oxygen. And notice what that is. What we're doing in terms of curved arrow patterns is what we're doing in terms of curved arrow patterns is a proton transfer. We're transferring an H+, which is just a proton, from one molecule to another. Okay, so once you have that, your molecule is now, and actually, so once you have that, this oxygen, instead of a lone pair, now has the hydrogen bonded to it. Because it has 3 bonds, it has a positive charge. Make sure you don't forget to draw that in. In general, in your mechanisms, the charges are important. these electrons snap back onto the oxygen, and so you just have water. Okay, now we do have a sort of resonance pattern here. Excuse me, we have a sort of resonance pattern here. We have a pi bond between atoms of differing electronegativity. And that's especially important here because of this positive charge, which needs to be stabilized. So we can draw the resonance structures. You would draw these big brackets to warn people that neither of these two structures inside here are the real structure. The real structure is only and always the average of the two. And to draw the other resonance structure, you take the electrons in the pi bond and move them onto the more electronegative atom. So when you do that, you get rid of that pi bond, you have a new lone pair on the oxygen. You'll notice that the carbon is now missing electrons. It lost the pi electron, so it has a full positive charge. And so you can almost, so now you just do another proton transfer. If you look at our original change, this oxygen didn't have a hydrogen. It does in the end. That's one proton transfer. That's the one we've already done. And then the second hydrogen is here in the beginning, but it's not in the end, so that has to go away. And so that's what we do here. This water can function as a base, steal that hydrogen, and the electrons can go to stabilize the positive charge there. This is another proton transfer. And after you have that, you will have your enol. So you have the alcohol on top, the OH, and then right next to it you have the pi bond, so that's the enol. And so when a ketone turns into an enol, it's called tautomerizing, because you're really just changing the position of one hydrogen. So keto-enol tautomerization, that's what this mechanism is. And it's really just two proton transfers. One to put the hydrogen on the oxygen, one to take it off of the carbon next door. Okay, so the whole point of this exercise is to get you to sort of train you to see how ketones and enols, or for that matter aldehydes and enols, are constantly in an equilibrium with each other. It's not necessarily an even equilibrium, but they're both always there. And so what will become really significant for this chapter is that what in the ketone does not look like it's especially nucleophilic, that alpha carbon, becomes that way because of those pi electrons in the enol. If it's acid-catalyzed, the enol, the pi bond, can act as a nucleophile and start attaching things onto that alpha carbon. And so the new thing in this chapter is the idea that the alpha carbon, this carbon right next door to the pi bond, and to carry it over, it would be right there, that alpha carbon can act as a nucleophile. So that's what we're going to see in all the reactions in this chapter. And it all starts with the idea of this keto-enol tautomerization when it's acid-catalyzed.